Hello everyone, I welcome you all to this class. Today we want to consider another example under this topic we introduced in our previous video, the mean value theorem. We stated this theorem in our previous class, and we also saw a particular example. That is, we showed that a particular function satisfies the hypothesis of the mean value theorem. So we have another function to consider today, and we want to show that that function satisfies the hypothesis of the mean value theorem. So let's consider this example we have here. What we have, they say show that the function f of x, which equals x plus 1 over x, satisfies the hypothesis of the mean value theorem on this closed and bounded interval 1, 2. So what we have to check, you have to check whether the function is continuous on the closed and bounded interval. So according to the mean value theorem, the function must be what? Continuous on the closed and bounded interval. So what is the closed and bounded interval we have? That's this closed and bounded interval 1, 2. So now look at the function you have. We have x plus 1 over x. Now looking at this function, any number you pick from 1 to 2 and substitute for x, you will always get what? Real numbers. You will always get what? Real numbers. You will not get infinity or undefined expression. And because of that, this function is clearly continuous on this closed and bounded interval. So let's make that statement. So look at what I've written down here. Since x is continuous on 1, 2, now look at the function you have. F of x equals x plus 1 over x. Now this function has two parts. That is, the first one is x, the second one is 1 over x. The first, what I'm saying is it has two parts, is that the first one is a polynomial, while the second one is what? A rational function. Rational function is a function in fraction form. Now you have to consider the continuity of this function based on these two parts of function. Now x, which is a polynomial, is continuous. We have seen that in our previous class. Polynomials are continuous everyone on the real line, so it must be continuous on this subset of the real number 1, 2. Then this rational function 1 over x, we know that if you have a rational function, a function in fraction form, you always demand that the denominator should not be 0 for it to be continuous. So clearly this 1 over x is continuous. Why are we saying it's continuous? Because this denominator, which is x is not 0 for all the numbers from 1 to 2. There is no 0 there. So this function 1 over x is always what? Continuous, because the denominator is not 0, right? So it's continuous. Since the denominator is not 0. So, and the sum of two continuous functions is continuous. So therefore this function is continuous on this closed and bounded interval 1, 2. So the next thing you have to check, you check differentiability, check whether it's differentiable on the open interval. The open interval I have is open interval 1, 2. So check whether the function is differentiable on this open interval. F prime of x is equals to, let's differentiate this function. Differentiate x, you get what? 1, right? Then differentiate 1 over x. 1 over x is written as x raised to power negative 1. Of course, we bring down the power, negative 1 times x raised to power negative 1. Remove 1 from the power. So you have negative 1, which is negative x raised to power negative 2, which you can use indices and return it to fraction form. So this will be negative 1 over x squared. So the derivative of 1 over x is negative 1 over x squared. So clearly you check whether the derivative exists on this open interval. Not if you put numbers between 1 and 2 and replace it for x here, you always, and solve this, you always get what? Real numbers, because this fraction, this rational function is continuous because x is not 0 here. So if x is 0, you'll be having 1 over 0, which is infinity. So x is not 0, so we cannot get infinity here, right? So therefore, so we are making this statement that this function is differentiable on the open interval because the derivative what exists. The derivative exists as you put numbers between 1 and 2 and substitute for x, you always get real numbers. You will not get infinity or undefined expression. Because of that, we say that the derivative what exists, so it's differentiable, right? We will have to get that point C such that f prime at C is equal to f at B minus f at A divided by B minus A. Let's first of all find f at B. F at B is equals to, f at B is the f at B is the last point. What is the last point of this? 2. F at 2. So you go to your function and replace x with what? 2. We still have our function written down here. We replace x with 2. So you have 2 plus 1 over 2. And if you solve this, you will now have 2 is same thing as 2 over 1. So our LCM is 2. Our LCM is 2. Then 1 divided 2 is 2 multiply 2, 4. Plus 2 divided 2, 1. Multiply 1, 1. Of course, 4 plus 1 is 5. So we have 5 over 2. Then you check f at A. F at A is f at the first point. A is the first point. What was the first point here? 1. You replace x with 1 in this our function. You have 1 plus 1 over 1, which is 1 plus 1, and which is what? 2. Now you now solve this. You now solve the equation f prime at C. What is f prime at C? Go to your derivative. This is our derivative. Replace x with what? C. Substitute x for C here. You will now have 1 minus 1 over C squared. And this is equal to what? F at B minus F at A. What is F at B? 5 over 2 minus, what is F at A? 2 divided by B minus A. What is your B? The last point, 2. What is your A? The first point, 1. So we have done this minus this. That's B is the last point and A is the first point. So this implies, so we have written down this expression like that. So this implies 1 minus 1 over C squared is equal to, let's simplify this. 2 minus 1 is what? 2 minus 1, you get 1. And 1 divide this quantity, you have this quantity back. 5 over 2 minus 2, right? So what do you have left? So this implies 1 minus 1 over C squared is equal to, let's solve this fraction, right? So the LCM, 2 is same thing as 2 over 1, so LCM is 2. 2 divided 2 is what? 1 multiply 5, I have 5, minus 1 divided 2, 2 multiply 2, I have 4. And this implies that 1 minus 1 over C squared is equal to 5 minus 4, you have what? 1. So we have 1 over 2, right? So what do? Let's move this to the other side and move this to this side, right? So this implies, let's move this to this side. 1 minus, because this positive half come to the left hand side, change to negative, equals, move this negative 1 over C squared to the right, you have positive 1 over C squared. 1 minus half is what? 1 minus half is half, equals 1 over C squared. What do? You cross multiply, right? Cross multiply. So cross multiply. So if you cross multiply, C squared multiplied by 1 is what? C squared. And 2 multiply 1, you have what? 2. So what do? You take the square root of both sides. So this implies take square root of c squared, you have c, equals take square root of 2, you have plus or minus square root of what? 2. Right? So this is equal to plus or minus 1.142 something, right? So let's take the approximation. This is approximately equal to, let's take the approximation, 1.142. So the two values of c we got, the one that is inside the open interval 1, 2 is this positive 1.142, because our interval does not have negative number. So negative 1.142 will not be there. So the c we are going to take is this one. Remember the mean value theorem says that there exists at least one point c. So we're able to find that one point, which is c equals 1.142, which lies inside this open interval. So we can say that the mean value theorem is satisfied. So let's make that conclusion here. Therefore, the mean value theorem is satisfied. So I've made the conclusion here. The mean value theorem is what? Satisfied. Thank you so much for being part of this class. See you in our next class.